Hey students, welcome to lecture number 7 of Linear Algebra 1. So today we want to talk about the inverse of a linear map, and in lecture number 3 we discussed what it means for a function to be invertible. So this was the case when the function is bijective, which meant it is injective and surjective. And in the last weeks we also discussed when a linear map is injective and surjective, and you calculated a lot of examples. So today we want to consider the case when a linear map is bijective, meaning it's also invertible, and then we want to ask ourselves if the inverse is also a linear map and how we can actually calculate it. So first, recall. So this is now recall of lecture number 3, where we discussed about functions. So if we have a function from a set x to a set y, then we said that this is invertible if we can find an inverse, meaning if there exists another function going in the other direction, a function g going from y to x, which will be the inverse of x, with a property that if I start applying f to some x, and then I apply g, so I first go from x to y, and then I go back by g, then this should be just x, and this should be the case for all x and x. And also the other way, meaning that f is also the inverse of g, meaning if I start in y, go to x, and then go back by f, then I should also end up again at the starting point, meaning that if I apply g to some y, and then f, then I should end up at y again. And this should also be the case for all y in y. And then this g is called the inverse of f. And the notation is that we write g is f to the power minus 1. So this doesn't mean we divide by f. This means, this is the definition of this notation, that this function with this property here is f to the power minus 1. And we saw that if f is bijective, this was exactly the case when f is invertible. And also these two properties here, we could say that if I compose the map f with g, then this is the identity on this set x, and the other one, if I first apply g and then f, so the composition of these two is the identity of y. And why was this the case here? So bijective means it's injective and surjective, so why can I find an inverse if f is bijective? So bijective means it's surjective, so this means in particular for every y in y, so somehow this part here corresponds to surjective. So for every element in y, so the image is y, and therefore for every element there, I can find exactly one. So this here means I can find exactly one x, a unique x in x, with the property that f of x equals y. And this here, that I can find exactly one x, this corresponds to the property injective. And if I have this, so this here is true for a bijective function f, so how can I construct the inverse? Where the inverse, so how do I define g of some y? Well, for every y, I can find exactly one x, and therefore I can define g of y to be this x. So I can use this property here to define the inverse, and therefore if a function f is bijective, it's also invertible because I can write down the inverse. And also the other direction you can check is true, that if you start with an invertible function, meaning satisfying this property here, then this function is also bijective and injective. So this is now for functions in general, but we are interested in linear maps, and for linear maps we already had a lot of examples for surjective and injective, but now we will be interested what is when this linear map is bijective, meaning when it's invertible. So first we will ask, when is this the case? So which linear maps are invertible? And if a linear map is invertible, then we have this inverse function. And the question is this function also a linear map? So this is the second question. And then in the end, we want to answer the question how we actually can calculate this inverse. Meaning if I have a linear map, this always means I have a matrix of this linear map. How can I construct the matrix of the inverse? Okay, so let's start by doing one example. So let's consider the following linear map from R2 to R2, which sends a vector x to this here. So we just multiply by this matrix 1, 3, 2, 4. And now we can ask, is f invertible? And what do we need to do? Well, so we need to show that for any y in R2, we need to check. Oops. Check if this equation f of x equals this y has a unique solution. Because then the inverse of this linear map f is defined by sending this y to this unique x. And here that we can take any y means this should be surjective, and this unique means it's injective. So in other words, we can try again to solve this linear system here. And solving this linear system just means we consider this augmented matrix 1, 3, 2, 4, and here the vector y1, y2. And now we again want to solve this. So what we can do in this case here to get rid of this 2 is by subtracting the first row from the second twice. So then here we have 1, 3, y1. Here we have 0, and subtracting 6 from 4 is minus 2. And here we have minus 2 times y1 plus y2. And now we can make this minus 2 to a 1 by dividing by minus 2 here. And then we get 1, 3, 0, 1. And here y1. And now I have plus 1 y1 and minus 1/2 y2 here. And now we just need to get rid of this 3 here by subtracting the second row 3 times from the first. And this gives then here 1, 0, 0, 1. And here 1 y1 minus 3 times y1 is minus 2 times y1. And here I have minus 3 times minus 1/2. So this is plus 3/2 y2. And the second row is still the same. And here we see that for an arbitrary y1, y2, we now have a unique solution given by x1 equals this here and x2 equals this here. So get solution, unique solution x1, x2 equals minus 2 y1 plus 3/2 y2, y1 minus 1/2 y2. So in particular here we see that this map is surjective because this works for any y, and it is also injective because we don't have any free variables here and we get a unique solution. And so for a given y we get an explicit x. And this here we can also write by the matrix minus 2, 3/2, 1, minus 1/2 times the vector y1, y2. And this here will be exactly the inverse, because for the inverse what we want to find is now the assignment given a vector y, we want to find the unique x. And here we have exactly the formula for x, which is given by multiplying this vector y with this matrix here. So the first observation is that f is invertible, because we have this, for every y, we have this unique solution x. And the inverse we can read off here. So the inverse of f. So this is now f inverse, which goes in the other direction. Well, in this case, the set x and y are both R2, but we still go from R2 to R2 by sending a vector y1, y2 to exactly this part here. So we multiply with this matrix. And in particular, we see that this is also a linear map because it's just multiplication with the matrix. So here, in this case, the inverse is linear. And this here is the matrix of the inverse. So this is the matrix of f inverse. Okay, so in this case, we answered all these three questions well. So in this case, we just checked that this map is injective and surjective. And we saw that in this case, the inverse is also linear. And we calculated this by just solving this linear equation. Because here, in general, the inverse we can define like this. So if for a given y, if we can find the unique x with this property, then we can define the inverse by sending this y to this unique x. And this is exactly what we did here. We started with some y, we got some x, and then the inverse is defined by sending this y to this x. Okay, but now in general the question is, when is it possible for a linear map to be invertible? And here we saw, here we have a map from R2 to R2. And surjective means that we can find a solution for any y. And injective means that we don't have any free variables here. So for example, imagine if we would have maybe a map from R3 to R2, then we would still have 2 rows, but 3 columns. And then it's actually not possible to not have free variables. So in this case, it couldn't be injective. So in general, we will see that these two numbers actually need to be the same in order to be invertible. And this is a statement of our first theorem, namely a linear map f from Rn to Rm is invertible if and only if this m equals this n, and if both of them equal the rank of f. And we didn't really define the rank of a linear map f, but what we mean by the rank of f, so the rank we just defined for a matrix, and the rank was given by the number of pivot elements in the row-reduced echelon form of this matrix, and the rank of a linear map is, as you might guess, defined as by the rank of its corresponding matrix. And the statement is if the number of rows equals the number of columns of this corresponding matrix, so in particular this n needs to be m, and if this equals the rank, then this linear map is invertible. So here we need to show 2 directions. So we want to show that if f is invertible, then this n needs to be m, and it needs to be equal the rank. And also the other direction, if the rank equals m and n, then this map is invertible. So we want to prove this direction, and we also want to prove this direction. So let's prove this. And first, a general observation. So f invertible, so this was equivalent to that this linear system here, fx equals y has a unique solution for all y in Rm. And how do we find this? Well, we start with this augmented matrix Fy, and then we do some row operations, and in the end we end up with a, so here will be the row reduced echelon form of this augmented matrix. And so on the left hand side we will have some b, so b is the row reduced echelon form of this f, and here the last column will be some vector z. So this b is the row reduced echelon form of the matrix of f, and this z, where this z will be will depend on this y, but we want to solve this linear system for all y's. So actually this z will be also be an arbitrary vector in Rm. So this will be a vector in Rm. So this can be arbitrary. Because we consider this equation here for all y's in Rm. Okay, so now let's prove this direction here. So let's assume f is invertible, and then we want to show m equals the rank of f. So let's go this direction. So suppose f is invertible, so now let's assume that the rank of f is actually smaller than the m. So first notice the rank of f cannot be larger than m, because the rank of f is the number of possible pivot elements here in this matrix. And of course, if the number of rows, so the number of ones here cannot be larger than the number of rows. So this rank of f is smaller equal than this m, but we want to show that they're equal. So now let's assume that it's actually smaller. So if the rank of f is smaller than the number of rows, so how does this look here? So how does this look like? So Bz will be some matrix. So here we have the z, and if the rank is smaller, this means that there are some rows here which do not contain a pivot element, because this is exactly the statement here. So there will be some rows here which are 0, and then there's some rest here. And this whole thing is has this size m. But if we have this, then we will see that for some z there will be not a solution, namely for those z where we have some entries here. So this would mean no solutions for some z's. So in other words, for some y's, because this z depends on this y here, so there will be, if there's a z with some entry here, then I can also find a y which will lead to this z with some entry here, and then for this y we will not have a unique solution of this linear system here. But this is a contradiction to the assumption that this f is invertible, and therefore this cannot be the case. Therefore, so this is a contradiction, and therefore we see that the rank of f actually needs to be the same as m. So it cannot be smaller than m. So now we have that this m equals the rank of f, and now we want to show that also the number of columns equals the rank of f. So again, if the rank of f, which cannot be bigger than the number of columns, because otherwise, I mean, for each column I can just put in one pivot element, but it can also be not strictly smaller, because in this case, how does this BZ look like? Well, in this case, this means, so here I've got the Z, and here this size is n, and if the rank is smaller than the number of columns, this means I have less pivot elements than columns, and this means, so maybe here I have some pivot elements, but at some column I cannot have any pivot element. Maybe here I have again. So this means there's a column without a pivot element, but this would mean that I don't have a unique solution, because then this column would correspond to a free variable. So in this case there are columns without pivot elements, and this would mean no unique solution. So no unique solution. And therefore this is a contradiction, because we assume that f is invertible, and f invertible means that for any y we have a unique solution, and therefore this rank needs to be the same as n. So this is one direction. So we showed now that if f is invertible, then the rank of f equals m, and the rank of f equals n. In particular, this means that this n needs to be the same as the m. So there cannot be a invertible linear map from an Rn to an Rm if the m and n are different. Okay, so now the other direction, which is actually quite simple. So now let's assume that the rank equals m and n, and we want to show that this f is invertible. So let's go the other direction. So if this m equals the rank of f, so what does this mean? How does this B look like? So the B is a row-reduced echelon form of the matrix of F. And now the statement is the rank equals the number of columns and rows, but this just means that this B then is just the identity matrix. So first of all, it's a square matrix, and the number of pivot elements, so in each column I have a pivot element, and therefore this is identity matrix. But in this case, it's clear that I will have a unique solution, because every time I have the identity matrix here on the left-hand side, then for any y, I will have a unique solution. So this equation, f of x equals y, has a unique solution for all y's, and this means f is invertible. And this proves the theorem. Okay, so now let's see what happens if we have a linear map which is invertible, meaning we have an inverse map or inverse function, and then the next question is this inverse also a linear map? So this will be the next proposition, and the statement is yes it is. So if I have a linear map from Rn to Rn, so now we can assume that this m equals n, because we saw before that the only way to have an invertible linear map is if these two numbers are the same. So now let's say I have a linear map from Rn to Rn which is invertible, and then the statement is the inverse going in the other direction is also linear. And to show that something is linear means we need to check these two conditions. So let's prove this. So let's take u and v in Rn, and we now define x to be f inverse of u and y to be f inverse of v. I mean, we know f is invertible, therefore the inverse exists, and I can apply this inverse to this vector u, and I can apply this inverse to the vector v. So in other words, this u is just f of x, and this v is f of y. Okay, and what we want to show is what is f inverse of u plus f inverse of v. We want to show that this is f inverse of u plus v. So this, by this notation here, is just x plus y. And x plus y is the same as applying the identity to it. So, and the identity is given by f inverse and f. So if I apply first f and then f inverse to x plus y, then this is the same as x plus y. So here I could also write this circle, but we also last time used this notation that if I compose two functions, we can just write it like this. And at the beginning I said inverse means that if I compose them, this is just the identity. So this here is the same. But now, so here I could also write it like this. So I apply f inverse to f of x plus y. And now we can use that f is linear. So inside this f inverse here, I can write this f of x plus f of y. And this, because f of x equals u and f of y equals v, is just the same as f inverse of u plus v. And this is what we wanted to show. So f inverse of u plus f inverse of v equals f inverse of u plus v. And now we need to check the second condition, where we have the scalar lambda. So we want to see what is lambda times f inverse of u. And with the same trick, this is just a lambda of x. And here I can again apply f and then f inverse. And here inside I use that f is linear. So this here is lambda times f of x. And f of x is f of u. F of x equals u. So this is just f inverse of lambda times u. And this is the second condition, that f inverse of lambda u equals lambda times f inverse of u. So therefore, the inverse of a invertible linear map is also linear. So now, this now raises the next question, because every time I have a linear map, I also have a matrix attached to this linear map. So if I start with an invertible linear map F, then due to this proposition, the inverse exists, and which is also linear, then we can ask, what about the matrix of this linear, of this inverse here? And this will get a name. So here, so if I have a matrix A, which is a matrix of some invertible linear map F, so in other words, this A equals the matrix of F, then we define the inverse of this A, which we denote by A inverse, to be the matrix of the inverse of the map F. So in our example at the beginning, here, if this is a matrix A, then this here is A inverse. Because here this A is the matrix of a linear map F. And then we calculated what is the inverse. The inverse is again a linear map, and the corresponding matrix here, we say this is the inverse of this matrix A. So when does this exist? Well, we saw before that, so the question is when I have an n by n matrix, so it needs to be a square matrix, because otherwise, if this would not be a square matrix, then this would correspond to a linear map which doesn't go from Rn to Rn. So by this theorem we saw before, this invertible matrices need to be square matrices. So and if I have a square matrix, I can ask myself, when is this invertible? And therefore what I want to solve is this equation ax equals y, and see that this has a unique solution for any y. And this then just corresponds to the fact that that a matrix is invertible, or the inverse of a matrix exists. And we also say this is then invertible if and only if the row-reduced echelon form of this matrix is the identity matrix. Because this exactly corresponds to this fact here that I start here with the matrix A, do some calculation, and here the left-hand side here is the row-reduced echelon form of this matrix A. And here this linear system has a unique solution for any y exactly then when this part here is the identity matrix. So there cannot be 0 rows, because otherwise this wouldn't have a solution for any y, and it also cannot contain 0 column, or a column without a pivot element, because then it wouldn't be unique. So therefore the only chance for this linear map to be invertible, so in other words the corresponding matrix has an inverse, is when the row-reduced echelon form of this matrix is the identity matrix. So this is therefore an easy criteria to check if a matrix is invertible. And if you do this calculation, you actually also calculate the inverse. And there are also some properties of the inverse, which we will not prove, but which you can check by yourself following from the definition. So first of all, if I multiply a matrix with its inverse, then this is the identity map. And this just corresponds to the fact that if I have a f and I compose it with f inverse, well, we saw that this is the identity matrix. So this is the identity map, and the matrix of this, so this is the identity map on Rn, and the matrix of this is the identity matrix. And last time we saw that the matrix of the composition of two maps is just given by the product of the corresponding matrices. And therefore you see that the product of a matrix and the product of the inverse matrix is exactly the identity map. So this gives this statement here. And also because I can swap this order here, we also see that A inverse times A equals the identity matrix. And also another statement is that if I have two n by n matrices, and if they are both invertible, then if I multiply them, B times A, then the first statement is that this product is also invertible, and the inverse of this product of two matrices is exactly given by changing the order and taking the product of the inverses. So here you can check that you need to change the order, because if I want to multiply this from the left with the inverse, so this here is, then you first see that because the product of two matrices is not commutative, so really I cannot change the order of multiplication here. So therefore I need to inverse here the order, such that the B inverse gets first multiplied with B, which then gives the identity matrix, and then I can multiply this A inverse with A. And therefore this matrix here is the inverse of this matrix. Okay, and now well, we saw one example, but in general the question is how can we actually determine the inverse of a matrix A. So one way would be solve linear system. So this we did in example 13. And similar to this, but a little bit more systematic, so maybe let's go back here to this calculation here. So if I started with this matrix here and ask how can I calculate the inverse, well, then I can write it here on the left side, and here I write an arbitrary vector y1, y2, do these row operations, then end up here with the identity matrix, and on the right hand side I have this this vector here which has entries depending on y1 and y2, and then from this vector I can read off again as a corresponding matrix, and then I would get the inverse. And this we can do a little bit more systematic, but it's exactly the same calculation. So therefore let me steal this here, copy. So this here is the calculation we did before, and I erase some parts. Maybe this I can put there. So this is this. And here's some parts missing. Okay, and so in general, if we want to calculate inverse of A, let's say A is an n by n matrix. We consider the following augmented matrix. So this is now a more general form of an augmented matrix as we did before. So before, augmented matrix meant that we take the matrix A here and put a vector here, and but instead of putting a vector here, we will now put a matrix there, and more precisely we will put the identity matrix there. So if I have a matrix A, I will put it here, then we again draw a line, and here we now put the identity matrix. So this in total will be a n times 2n matrix, because this here is also an n by n matrix. And what we will do for this n times 2n matrix is again calculate the row reduced echelon form. So after some row operations, we will see that on the left part we will have the row reduced echelon form of A. And so if A is invertible, this means we will have now the identity matrix on the left hand side. So this here is the row reduced echelon form A. And then there will be some stuff on the right hand side, and this matrix here on the right hand side will be the inverse. And let's do this with this corresponding example here, and you will see this is actually exactly what we do here. So, but instead of putting a vector here with y1 and y2, we will have the identity matrix here, which corresponds to 1 times y1 and 1 times y2. And then in the end here we will have a matrix where we have -2 here, 3½ here, and so on. But let's do this. So this is example 14. So we want to calculate the inverse of this matrix again, 1, 2, 3, 4. So what we do is we write the matrix here. So in this case n equals 2, so we consider this matrix here, 1, 3, 2, 4. And here is the identity matrix of size 2. But now we do, well, exactly the same operations as before. -2 times this there. So we have 1, 3, 1, 0, 0, -2, and here -2, 1, and then here times -1/2, 1, 3, 1, 0, 0, 1, 1, and -1/2, and -3 times this there. So we have 1, 0, 0, 1, and now 1 minus 3 times is, so minus 2, 0 plus 3 half, so this is 3 half, 1 and minus 1 half. And now you see this is exactly, so on the left hand side we have the identity matrix of size 2, and on the right hand side we have a 2 by 2 matrix, which in this case is exactly this A inverse. And actually if you compare these two calculations with the original one, you see it's exactly the same, but maybe it's a little bit cleaner because we don't deal with these y1 and y2, and maybe this is a better way to do this. So anytime someone asks you to calculate the inverse of a matrix, so maybe in daily life this will not happen so often, but if I ask you to calculate the inverse of a matrix A, what you need to do is we write the matrix A here on the left hand side, and on the right hand side you put the corresponding identity matrix, and then you just bring this matrix here to reduced echelon form, and then on you will see that if you end up with the identity matrix here on the left hand side, then the first observation is, well, okay, this matrix you started with is invertible because the reduced echelon form is the identity matrix, and then the rest here on the right hand side will be the inverse of this corresponding matrix here. And now let's check in this example here also that this satisfies this property that if I multiply the matrix A with the inverse, that I get the identity matrix. So here you can check that if I multiply A with A inverse, so here it's 1, 3, 2, 4. So multiplying matrices we learned last time, so this just meant that I multiply this matrix with each column here. So if I multiply this matrix with the first column, we see, well, 2 times 2 plus minus 2 times 1 is minus 2, plus 3 times 1 is 1. And here, this times this gives 0. And here, this times this, 3 half minus 3 times half is 0. And here on the bottom, we get 1. Which in this case is exactly I2. And you can also check if you multiply it the other way around, you also get the identity matrix. Okay, and now finally some remarks. So this is the way you can calculate the inverse of a matrix. But there's also another interpretation of these row operations. So going from this matrix here to this matrix, so what we do is we subtract the first row twice from the second row, and this operation here from there to there can also be described by multiplying with a matrix. And these matrices are called elementary matrices, and so this is just a remark, and this we will do in more detail in linear algebra 2 when we talk about the determinant of a matrix, and there we will learn that the determinant of a matrix is exactly non-zero when this corresponding matrix is invertible, and to prove this we will use these elementary matrices. But the statement is, so there are 3 types of matrices which correspond to these 3 row operations, and the first, so if I have a lambda, a scalar lambda, and I have so we consider these n by n matrices here, then the first type of elementary matrices is given by this matrix here, which has 1s on the diagonal, and here in row I and in column j I have a lambda, and this matrix we denote by r lambda j I. So this is the first elementary matrix. The second is denoted by r lambda I, which just means I have 1s on the diagonal, but here in row I and column I have a lambda. And the last matrix is this matrix here, which is again the identity matrix, except that here I have I mean here in row I have a 0 on the diagonal, and in row J I have a 0 on the diagonal. But then here in column I and row J I have a 1, and here in row I and column J I have a 1. And the statement is that multiplying with an elementary matrix from the left corresponds to these row operations. So the first statement is that if I multiply from the left with this matrix here, then what this does is, so if I have a matrix A and I multiply it from the left with R lambda J I, then this product of these two matrices is exactly the matrix I get by adding lambda times the row J to the row I in the matrix A. And similar, maybe this here is clear that if I multiply this matrix with a matrix A, so everything stays the same except in row lambda I multiply, in row I multiply with this number lambda. So this corresponds to these row operations R2, and this matrix here just interchanges the row I and row J if I multiply from the left. If I would multiply from the right, then these matrices would do something with the columns, but if I multiply from the left, then these matrices do something with the rows. And this I want to make clear in our example we use the whole time. So let's start again with our matrix A, which in our example was the matrix 1, 3, 2, 4. And the first operation we did to this matrix was that we subtract the first row twice from the second, and then we got the matrix 1, 3, 0, minus 2. And going from there to there, so how can I go from this matrix to this matrix? I can multiply with the matrix from the right, from the left, sorry. And so this here corresponds to row operation 1. And so I want to multiply with the matrix R minus 2. So I take the first row and add it minus 2 times to the second row. And the corresponding matrix is, I have 1s on the diagonal and a lambda there. So in this case, I have 1, 1, 0, minus 2. So let's check this. If I multiply this matrix 1, 0, minus 2, 1 with the matrix A, 1, 3, 2, 4, what is this? Well, I multiply this with this here. So you see in the first, if I multiply this, I doesn't change the first entry here. But the second entry is given by taking the first entry here, so from the first row times minus 2, and add it to 1 times the second row. So this is exactly that I take this entry here and subtract it twice from there. So this is 0. And also to get this column here, I multiply this matrix with this. So again here, if I multiply it with this, the first row stays the same. And in the second row, I multiply this with this. So I take 1 times the 4 and minus 2 times the 3. So what I do is I subtract twice the 3 from the 4, and I get the minus 2. So therefore this row operation here really corresponds with multiplying with this matrix here. So then the next step was we multiply by minus 1/2. So to get 1, 3, 0, 1. And this now corresponds from there to there. We can multiply from the left with a matrix where we have minus 1/2 here. So this here is now a matrix of this type here, because we do row operation 2, where we multiply a row with a number lambda. And so this with this notation would be R minus 1/2, 2. And then the last row operation was that we take minus 3 times the last row and add it there to get the identity matrix. So from there to there, we multiply from the left. And now we have minus 3 here, because this is now minus 3 times the second row we add to the first row. And here in the end we have the identity matrix. So this is I2. I need to hide the spoiler. But so what we see now is, if I start with the matrix A, then I can multiply. First I multiply with R minus 2, 1, 2. Then I multiply with this minus 1/2, 2. So with this elementary matrix, and then I multiply with this minus 3, 2. And then in the end I have the identity matrix. So this matrix, this product here of matrices is again a matrix, so I could multiply these 3 matrices together. And the property is that if I multiply this with A, I get the identity matrix. So therefore this product here is exactly the inverse of A. And you can check that if you multiply this matrix here with this matrix times this matrix, where you need to be careful with the order, because the order matters, then you get exactly the matrix we had before, this minus 2, 3/2, 1, minus 1/2. And you also can check that these elementary matrices are all invertible, because this lambda is non-zero. So the inverse, for example, of this matrix would be the matrix where I have 1 over lambda in this position here. And here this matrix is its own inverse, and here this matrix is by having a minus lambda there. Yes, and therefore, if I start with the identity matrix, then I could also go in the other direction by multiplying with these matrices, and then in the end I could write this A as a product of elementary matrices. And the statement is that any invertible matrix can be written as a product of these, every invertible matrix is a product of these elementary matrices. So you can think of these elementary matrices as somehow the atoms of invertible matrices, because if a matrix is invertible, then I can write it as a product of these elementary matrices. Because invertible, we learn, means that the rowless echelon form of a matrix A is exactly the identity matrix, and to get the rowless echelon form, we do these row operations, and row operations correspond to multiplying with elementary matrices. So this is the first remark, and the second remark is that there exist explicit formulas for inverses of matrices. So if I give you a 2 by 2 matrix, for example, so first of all, this is called Cramer's rule. So if you look it up at Wikipedia, you can find there's a general formula for an arbitrary n by n matrix. So for example, if A is the matrix A, B, C, D, then this formula says that the inverse of A can be written as follows, as 1 over AD minus BC times D minus B minus C A. And you can check that if you multiply this matrix with this matrix, you get the identity matrix. But you also see that this expression here just makes sense if AD minus BC is not 0. And this makes sense because in the homework 2, exercise 3.2, you showed that a 2 by 2 matrix has rank 2, meaning the rowless echelon form in this case is exactly the identity matrix, is if and only if this AD minus BC is not 0. So therefore, here the condition is, so today we learned that if the rank is 2 of a 2 by 2 matrix, then this matrix is invertible. And here we can also see that this makes sense with this formula, because then we can write down the inverse explicitly by this formula here. And yes, so this here is also called what we will do in linear algebra 2. So this is a determinant of a matrix A. And in general, we will see in linear algebra 2 that if the determinant of a matrix A, which is some number, is not 0, then you can invert this matrix. And this general formula here uses also the determinant and divides by the determinant of the matrix A, and therefore it just makes sense if the determinant is non-zero. But if in real life you want to solve a linear system, maybe you do some experiments and you want to solve a linear system, or in engineering you have some big matrices you want to invert, then actually you would never use this Cramer's rule, because this is not good to implement, or in other words, this is so-called numerically expensive. So there are better ways to solve a linear system than using this explicit formula for the inverse. But maybe here in the 2 by 2 case, this is okay. Okay, so next time we will talk about subspaces, which are also a really important topic. And we will do some examples for inverses in the next homework and also in the next tutorial. See you then.